Good evening, students. So we in the previous class we saw the flexibility influence coefficient and stiffness influence coefficient concept. We derived potential energy using these coefficients. Even we extended this concept for continuous system in the form of functions. Now today we will continue this same concept. We will derive the Lagrange's equation in matrix form using these coefficients, and then we'll take up some examples. So let us see the slide. Yeah, so I was just explaining that once we have the concept of the flexibility influence coefficient, element that is having this form. Hello? Any issue? Hello? Hello? Can you able to see the slides, I hope?
No, sir, we are not able to see the slides.
You're able to see, no?
No, sir, no.
But I already shared. I'm sharing that. What has happened? You're not able to see?
No, sir.
No, sir. No, yes, sir.
Okay, maybe internet problem is there, it looks. So now you can able to see, no?
Sir, I think, yes, sir.
Okay. So this was the slide I showed yesterday also. Okay. What is happening? Why I'm not able to see? Okay. So this is the Lagrange's equation I was discussing in the previous class also. In a matrix form, and the representation of this I've explained in the right side, that each vector is having n components. So if we expand, that will be very cumbersome. So this kind of representation has been used to represent this expanded form of the equation. Now we know the kinetic energy can be expressed in this form, in which this is the mass matrix, which contain the mass influence mass coefficients, and this is called inertia or mass matrix. As I mentioned, this is having of the form of quadratic because the dot square term is there, and we know that kinetic energy is always positive, only zero when velocity is zero. So this is called positive definite quadratic form of the kinetic energy. This kinetic energy expression in the expanded form, and then how it can be clubbed in a vector and a matrix form is shown here, which again q dot vector can be represented like this. So I mentioned transpose of this because it is a row vector, and here is a column vector. Similarly, for the potential energy, we can able to write this kind of summation into the matrix and the vector form. So gradually we will be converting all the equations in the vector and the matrix form so that the handling will be easier. So this is the potential energy, this is the kinetic energy in the vector form, in the matrix form. So potential energy is also having quadratic form, but positiveness I will explain subsequently, because it's not always positive. In some cases there are some specific cases are there, so we'll take up that as we'll encounter the specific case. So now in the Lagrange equation, this particular differentiation is there. So I think I stopped at this point of time in the last class. So this differentiation of kinetic energy expression is this. I think I'll take the next slide, then it will be more clear how I got this. So this is the kinetic energy. So when I'm differentiating the kinetic energy with respect to the velocity, because the kinetic energy is containing two velocity terms in the product form, so we'll be having first differentiation of this with respect to velocity mass matrix, and the second as it is, then the first and two vectors as it is, third will get differentiated with respect to the velocity. Because this is a product form, so two terms will come from this. Now if you see the differentiation of the q dot vector, which is a row vector, with respect to the one of the velocity qr, I've explained here. So q dot, if we expand, there is q1 dot, q2 dot, qr dot, like this. And the differentiation of this with respect to qr, if we do, you can see that all terms will be 0 except that qr dot, that will be 1. So this particular vector, which is having all elements 0 except that rth row is 1, can be represented as delta IR. But IR is a delta IR is a Kronecker delta function. You can see here. It's a Kronecker delta function. The property of this is equal to 1 when I is equal to R, and is 0 for rest of the value of R. So this is the representation of this vector. It indicates that only the rth row is unity, others are 0. Similarly, this, if we take the differentiation of this, transpose of this, so this similar, exactly same, because this is a transpose, so this we are carrying forward. If I want to remove the transpose, that means I need to represent by L and opposite L sign, that is a row vector. So that will indicate that is a row vector with all elements 0 except at I is equal to R. So this is the differentiation representation basically in the expanded form. So once I'm saying I'm differentiating a vector q dot with respect to qr dot, then that means there is coordinate delta IR. So this simple extension of this. So in the previous slide, if you see, this I have done because velocity is here, so I'm differentiating this first. So I'm getting coordinate delta IR here. Any issue?
Yes, sir. In between, we are not able to hear you.
Okay, I think net issue is there, it looks. So, okay, I'm continuing. I think if you miss something, you can see in the video also. Because net is there, so I cannot, because whether it is a problem here or at your end, I don't know. Okay. So, because I can hear you clearly. So here Maybe you can mute. So here, when I'm differentiating, so now it is clear that the first Q dot will be chronological delta IR. Second case, second term here it will be that. And again, I will go to the next slide. Here, this is the differentiation. Now, if you see this particular, both the terms are basically because the mass matrix is symmetric. So the term here and here is equal. So that means we can take one of them and add. So half will go. So I'm taking one of them. That means the first one. Because this is valid for when the mass matrix is symmetric. And that's why we have the system in which most of the time mass matrix and stiffness matrix are symmetric. Otherwise, we cannot able to perform this. So this we added. So we got this term. And now if we multiply a full mass matrix having n by n size with a row vector having element 1 at rth row and rest of the 0. So this will become a row vector, and the rth row of the mass matrix will be there. So this within the box term will give us rth row mass matrix and q dot. So differentiation of the kinetic energy with respect to the velocity term is giving me a rth row mass matrix and the velocity term. So now you can see here. So when I'm doing this operation, I'm getting the rth row mass matrix into the velocity dot of the rth. And here r can be 1 to n. So anyway, when we combine them in a matrix form, they will go away. So now I'm combining them. Okay. So here I combined them all the r. So once I'm putting in a bracket, that means is having n components. Whatever I got, mr the row vector, and this I have put again in a bracket. That means I have stacked these all 1 to n. So you can see this QR is common. This will come out from this, and within this mr will be m1, m2, m3. These are the row vector of the mass matrix 1, 2, r, n. So that means if we see this becomes a mass matrix again. So when we combine all the terms of this particular thing, again we are getting the mass matrix instead of the row of a particular of the mass matrix. So when we combine all them, we got the mass matrix and QR dot. Now, because in the Lagrange's equation, the time derivative of that particular term is also there. So if we differentiate, mass is constant, so that derivative will go to the QR double dot. So the first term of the Lagrange's equation is giving us mass into acceleration dot, so mass matrix and the acceleration vector. Because time, this kinetic energy mainly depends upon velocity. So the term, the Lagrange's equation, this term will be 0. This is also in a vector form. So we have combined all of them in a vector form. Similar lines, we can take up the potential energy. If we differentiate, because potential energy will be having quadratic form. So the first term, this will be differentiated, and then second, this will be differentiated. Both are equal, so we can add them up. So we can take one of them, and then within the box term will give us a row vector of the stiffness matrix. And this expression we can able to write for r is equal to 1 to n. So n such expression we can write, and if we combine them again in a matrix form or vector form, then this row vector of the stiffness will give a again stiffness matrix directly, as I showed for the mass matrix. So this also appears in the Lagrange's equation, and the potential energy differentiation with respect to the generalized coordinate gives us this stiffness matrix into Q. So if we substitute all this differentiation in the Lagrange's equation, which we had here, this term was giving us mass into acceleration. This term is 0. This is giving us stiffness into velocity, stiffness into displacement. So we got this equation of motion in a matrix form. So here, we have the Q is the generalized coordinate, and when this generalized coordinate, if we choose displacement of the masses, then we'll find that the mass matrix will be a diagonal matrix. But if we choose the generalized coordinate other than the displacement of the masses, then we may have the off diagonal terms in the mass matrix. Okay, so let me stop for a while. So I hope this any clarification in this. Otherwise, I'll take up one example. And yeah, Rakesh.
Look on the 15th page.
15th.
Yes, sir. Sir, in the equation of dou t by dou qr dot, sir, how did the both terms become equal? Actually, M is symmetric, but
Yes.
is delta IR transpose and delta IR equal and Q transpose and Q same?
Yeah, because if you multiply them, you expand this and you expand this, they will be same. I have not shown that expansion. But if we expand this, and they'll be same only when mass matrix is symmetric. Okay. Because one is pre-multiplied, another is post-multiplied. Swapping is there between this, but quantities remain the same. The right side of the mass matrix and the left side of the mass matrix. So unless the mass matrix is symmetric, this will not be true. Okay.
Thank you, sir.
Yeah. So any other question? Otherwise, I'll take one example. How to obtain the influence coefficient, flexibility influence coefficient, and how to obtain the stiffness influence coefficient. This particular example is quite lengthy, so I think a lot of concepts are there in this. So this example taken, you can see there is a shaft which is fixed at both the ends. Shaft is having no inertia, but in between there are 3 discs. So discs are having polar moment of inertia I1, I2, I3. The shaft is having flexibility in torsion. So you can see the disc 1, disc 2, disc 3 are having torsional vibration. That means it is twisting about its own axis, about its polar axis. So torsional vibration of the disc 1, theta 1, disc 2, theta 2, disc 3, theta 3. And because we are dealing with the torsion case, so the corresponding the elastic property G and J1 will come into picture, and I'll define what is the torsional stiffness using this parameter. So because here whatever the background you have, with that you can able to write the kinetic energy of the system, potential energy of the system. This is similar to something like a spring, mass, another spring, a mass, another spring, a mass, another spring. But spring is can be a torsional spring or it can be a physical spring. So here the springs are something like shafts, which we represent as spring of torsional stiffness. So this is a 3-degree of freedom system having generalized coordinate θ1, θ2, θ3. So I hope the problem is clear. So we can able to get the kinetic energy because the rotational energy of the disk 1, 2, 3 can be obtained. We are not considering the transverse vibration, so there is no up and down motion of this is taking place, or there is no axial vibration. Only the twist we are considering in this particular example. So the kinetic energy can be written, potential energy can be written because we can see the springs are having what kind of related twist based on that. So once we have the kinetic energy and potential energy, we can able to get the equation of motion and other things because that much background now you have using Lagrange's equation or Hamilton principle, we can able to get the equation of motion. So if you get the equation of motion, if you put them in a matrix form, the stiffness matrix will look like this, where K1, K2, K3 are stiffness of the first segment, second segment, third segment, and fourth segment of the shaft. So anyway, that equation of motion you can able to obtain, but my aim is to how to get the influence coefficient, the flexibility influence coefficient, and then it can be used in this kind of equations. So here's how we define the flexibility influence coefficient. So we define the flexibility influence coefficient like this. So here I'm representing the displacement at ith station due to force at jth station. So influence coefficient Ij is representing that when we have force at jth location, keeping all the force at all other locations 0, and if this force is unity, so this influence coefficient will be displacement at the ith station. In this example, the displacement is the angular displacement and force is the torque. So this expression which we are dealing with can be written like this, in which force is not torque and corresponding displacement. Now let us see this particular example which we are seeing. We are applying a torque at first disk, keeping torque at other disk 0. We are not applying any torque in the other disk. But when we are applying some torque here, some reactions at the support in the left side and the right side will come. So and that will be opposite to the whatever the torque direction we are applying at location 1. Now with this configuration, when we have applied only the torque 1, what are the influence coefficient we can get? We can get the influence coefficient A11, A21, A31. Let us see this in here. So here we applied the torque at J is equal to 1 because Tj, so J is equal to 1. So if I write J is equal to 1, so the above equation can be written theta I1 is equal to AI1 T1. So this is a very specific case when I applied the torque at 1, but I can vary from 1 to 3. That means I can get the displacement because of this torque at disk 1, disk 2, and disk 3. So this is represented as theta 11 is the displacement at disk 1. So that means I is equal to 1 is representing displacement at 1, I is equal to 2 is representing displacement at 2, and I is equal to 3 is representing displacement at 3. So the same equation, when I expanded I is equal to 1, 2, and 3 one by one, I could able to get the theta 11, theta 21, theta 31 relationship with torque T1. But they're related with influence coefficient A11, A21, A31. So these three influence coefficient, flexibility influence coefficient, I have written here. So when I'm applying the torque at one location, I'll get the influence coefficient with second subscript 1. So A11, you can see second subscript 1. In this here also, second subscript is 1. Here also, second subscript is 1. So that means if I want to apply the torque, unit torque at 2, I'll get all the influence coefficient containing 2 at the second subscript location. Okay, so that anyway it can be extended, but let us see how this 3 influence coefficient can be obtained in terms of the stiffness of the shaft segment 1, 2, 3, and 4. So this is the diagram which is showing because of this torque, what are the displacement at disk 1, 2, and 3. So here, as I mentioned, this is the displacement of 1. So theta 11 is representing the displacement at 1 because of torque at 1. Theta 21 is representing displacement at 2 because of torque at 1. This is displacement at 3 because of torque at 1. So second subscript is representing the torque location and first is representing the displacement location. This figure we'll see subsequently. This will be used to obtain the stiffness coefficient. So first we are trying to focus on the influence coefficient, flexibility influence coefficient. So once this is clear, what are the influence coefficient we are trying to find out by applying a unit torque at disk 1. Let us now go to the next slide. So the stiffness of the shaft segment K1, K2, K3 can be obtained using this. So Gj by I, Gj by Li. J is the this second moment of area, polar moment of area. For torsion case, it is pi d4 by 32. That you already know for torsion case. Here is the length of the shaft segment. So these are the stiffness of the 4 shaft segments. We can here K1, K2, K3, K4. These are the torsional stiffness of the 4 shaft segment in the system. Now we are applying torque T1 is equal to 1 here, keeping other torques at disk 2 and 3 0. In the previous slide, whatever the influence coefficient we defined can be arranged like this. So previous slide, this 3 can be used to obtain A11, A21, A31. So same thing I'm writing here. A11 is theta 11 by T1 because T1 is 1 because we have chosen unit torque. So this will be theta 1. A21 will be similarly theta 21. A31 will be theta 31. So influence coefficient can be obtained if we know these displacements, but still we don't know these displacements. So to obtain this 3 influence coefficient, any issue? Hello? Hello, mute yourself, please. Okay. I hope clear. Okay. So, our aim will be to obtain this theta so that we can get the influence coefficients. So now, as I mentioned, because of this torque, there is a the torque here. I should write the L1 and R1. Yeah. So there's the torque reaction at the support because of this. So we can see that this torque will be equal to summation of the left torque and the right torque because they are reactions, so they should balance each other. So P1 is equal to 1 is we are assuming that should be summation of these two reaction torques at left support and the right support. Now if we see TL1, TL1, TL1 can be obtained because here what is the stiffness of this K1 and the displacement of the disk 1 is theta 11. So if we multiply K1 with theta 11, that will be equal to TL1 because here if we are ignoring the right part, we know that here theta 11 displacement is taking place. So if we give that much twist to this spring of stiffness K1, we will get the torque which is there at the reaction. So this is the pattern like that. Same thing if we see the right side, forget about the right side of the disk 1. So if we know that displacement here is theta 11, so all the springs which are connected in series, if we apply theta 11 here, so theta 11 multiplied by the equivalent stiffness of all these three will give us this torque at right one. So here K2, 3, 4 is representing the equivalent stiffness of right side of the disk 1, whatever the stiffness is there, multiplied by theta 11 will give the uh, torque at reaction torque at the right one. And this equivalent stiffness of this three can be obtained because they are in series like this. So if they can be simplified like this. So the summation is from 2 to 4 because we have 3 because we are taking from the right of the disk 1. So 2, 3, 4 summation. So we related the reaction torque at left and right with the theta 11, and the stiffness is related like this. So again, the aim is now we'll substitute this here, both. And now you can see that we are relating the angle theta 11 with the stiffness, which stiffness of the shaft segment, which is our main aim to get the theta 11. And once we get the theta 11, A11 can be obtained in terms of stiffness. So in the next slide, I'm substituting this here and this here, so that yeah. So this is the same expression. So I'm substituting this two here. The first term from this, second term from this is equal to 1. Now theta 11 is common here that I can take out, and I can remaining thing I can put in the right side. So theta 11 is equal to this, and because this is inverse, I can simplify this. So this will go in the numerator also. And if we, because now if I take K1 common and I keep this within the bracket, so this term will be 1 by K, 1 by K1. So because here the summation is from 2 to 4, but if we can include this here, the summation will be from 1 to 4. So the alpha 11 we could able to obtain in terms of the stiffness of the shaft segment. The upper summation is from 2 to 4, lower one is from 1 to 4, and K1 is. So the first influence coefficient we could able to obtain using the theta 11 relationship. Now we'll aim for the second one, this one. So for that I need the theta 21. So I'm taking I think this is relatively easier as compared to this. So first I'm obtaining A31. So A31 is equal to theta 31. The torque was 0. Now theta 31 is what? This is the displacement of the third disk. Displacement of the third disk. So if we divide because if you see in this segment, the torque is TR1 in the right side. If I divide this torque with the K4, that will give us the displacement of the disk 3. So this has been done here. So if you see, this particular shaft segment is having torque TR because there's no in between some torque. In fact, the TR1 torque is there up to here. Okay, so at present I'm trying to see the displacement of the third disk. So that can be obtained by dividing the TR divided by stiffness, torsional stiffness of this. Okay, and TR1, previously we obtained TR1 as this K23 theta 11, which is theta 11. So here I'm substituting from the previous expression, and then theta 11 already we know is equal to alpha A11. So that has been substituted, and then alpha 11 also we obtained this. So if we substitute this here, and the K23 we obtained earlier. So that expression, so K23 expression from equation E, A11 equation from H, we substitute. After simplification, we get an expression of A31 in terms of the shaft segment stiffness. Now I will take up the next stiffness coefficient, that is A21, which is related to the theta 21. So theta 21 is the displacement of this. So now you see the displacement of this, either this can be represented as the torque at right side divided by the equivalent stiffness of these two shaft segment. So, or what we can do, we can divide this displacement of this as displacement of third disk plus relative displacement of second with respect to third. So this is the one, theta 31 is the displacement of the third disk, and theta 21 minus theta 31 is the relative displacement of these two. So either approach, either you divide theta 21 divided by the equivalent stiffness of this, or you divide this in two parts. And once I'm representing this as theta 31, this I already obtained earlier. Theta 31 is nothing but TR1 by K4, and this relative twist between these two can be obtained by TR1 because torque is common up to here, because we have torque at T1 here. There is change in torque here only, but remaining place the torque is same. So TR1 by K3, this one. So TR1 we already know. So if we substitute that here, we can able to get yeah. So this TR1 is common. So this if you combine, so this is nothing but the equivalent stiffness of the K3 and K4. So finally is turning out to be that. And TR1 we already know. This expression can be substituted here to get the A21, which will be this after simplification. Okay, so this is the three influence coefficient we obtained. If you have any questions on this, I'll take up. Otherwise, I can explain the remaining thing. If you have any question till now, the other concept will be similar to this. So getting influence coefficient is slightly involved, and sometimes people prefer to obtain the influence coefficient. People prefer to obtain the stiffness, which is easier as compared to the influence coefficient. So yeah, so there's no question. So I have explained how to obtain the influence coefficient, 3 influence coefficient when we apply the torque T1 here. Now to obtain the another 3 influence coefficient, we need to apply torque at 2 disk of unit value. So what I will do, I will skip this because the concept is similar. One by one you need to obtain. So and then in the next will be when we are applying the torque at 3 disks. At 3 disks it will be equivalent to the 1 because you can see that there is symmetry. This is in this end, this and this, and so on the similar line that we can able to obtain T3 also. So those influence coefficient I'm skipping here. I'm not explaining here. I'm giving the slides. If you have difficulty, you can again ask me the questions. So this is for the all 3 influence, all other influence coefficient. Procedure remain the same. Only thing is too much mathematics, so I'm skipping that. So this is for the third one. Okay. So now now this particular figure is for the stiffness calculation. Okay. So this is not for the influence coefficient. This is for stiffness calculation. In stiffness calculation, maybe I can go back to the very first slide. This one. So in place for obtaining the influence, the stiffness influence coefficient, what we need to, how we define that earlier, we defined by Fij is equal to Kij Uj. For this particular problem, F is torque and U is theta, so let us concentrate on this. So here we can define then Kij by giving a unit displacement at jth location. Unit displacement at jth location, and that will be the torque will give the corresponding stiffness coefficient. So let us see when the j location is first location. So we are giving a first location, the first location theta 1 displacement, keeping other displacement 0. Displacement at the second and third disk we are keeping 0. Only we are giving displacement at disk 1, which is 1. Theta is equal to 1. So j is equal to 1 is representing that we are giving displacement at disk 1, theta 1. So this above equation, if we put j is equal to 1, this will be Ti1 is equal to Ki1 theta 1, where I can vary from 1 to 3. That means torque will be there at first disk, second disk, third disk, they will be there. So if I put j is equal to 1 and I is equal to 1, that is the torque at first location. So K11 will be K11 into theta 1. So K11 is one of the stiffness coefficient. For I is equal to 2, K21. I is equal to, so here, okay. So here, because the torque is the reaction torque. Once we are fixing this will be reaction torque. So that particular torque will be opposite to the displacement which we are giving at this location. So that's why negative sign is coming here. So K and K21, because here I'm putting I is equal to 2. So K21 theta 1. And similarly, T31, this is minus, and so I'm just substituting the subscript. So here I'm substituting I is equal to 3. So using this, I can able to get the K11, K21, K31. So as I obtained in the previous case, the influence coefficient, now when I'm giving a unit displacement at the first location, keeping other displacement 0, I can get the K11, K21 and K31. So now with this concept, let us see how we can able to get. This is simpler as compared to the influence coefficient. So this figure is same here. So we are giving theta1 displacement at first disk, and so what is the torque needed to do that? And reaction, because we are fixing here. So once we are fixing here, this torque, whatever the displacement we are giving, so once we are fixing here, this will also remain fixed, or they will also not be having any displacement, and whatever the torque is here, the same is can be considered here. So now once we are fixing this, one reaction is TL1 here, and whatever the torque at the disk 2 we are seeing, T21, that will be also a reaction, because once we are fixing the second disk, it will come as a reaction at the disk location. So if you see the left part of this is the torque which is applied, and the displacement of this is 1. So that displacement into the stiffness of the first shaft segment will give me this torque. So TL1 will be displacement of the disk. That means whatever the displacement of this particular shaft segment is, theta1, which is equal to 1, and the stiffness of that, if we multiply, that will give the torque at this end. Similarly, torque at this end will be, because we are applying theta1 here, so displacement 1 into the stiffness will give the torque T21. Okay, and so these are the stiffness. Now, how the influence coefficient the stiffness influence coefficient have been defined on the very first slide, K11. So you should not confuse with the stiffness K1, K2, K3, 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 K4 with the K11, K12, K13. Okay, they are the matrix stiffness matrix elements. So, and they are the stiffness coefficients which we are trying to find out in terms of the stiffness of the shaft segment. So we define in the very first slide K11 as T11 by theta1. Now we are giving theta1 as 1. So that means K11 will be equal to T11. So our aim is to obtain the T11 so that we can able to get the K11. Okay. So in this figure, if we see this T11 we are applying, theta11 theta displacement we are giving. So to do that, we need to apply T114 torque here. That will be equal to the reaction here plus here, because this is also fixed according to the definition of the stiffness coefficient. This must be fixed. So this should be T11 should be equal to this plus this. So this is the expression T11 is equal to TL1 plus T21. And T11 in the previous slide, okay, T11 is K11 and TL1 is K1, T21 is K2. So that has been substituted here. So this was K11, K1 and K2. So here you can see that K11 coefficient, which is of the matrix stiffness matrix, is expressed in terms of K1 and K2. So K11 is equal to K1 plus K2. Similarly, the influence coefficient, stiffness coefficient K21 we define as minus of T21 by theta1. T21 by theta1. Theta1 is 0, theta1 is 1, so this becomes 1. K21, in the previous slide we obtained K21 as K2, T21 as K2, so the influence coefficient K21 it becomes equal to minus K2. Okay. Similarly, K31 influence coefficient, stiffness coefficient we define as minus of T31, theta 1. Theta 1 is 1. T31 is displacement torque here. But once we have fixed here, there will not be any torque here. So that will be 0. So K31 will be 0 because once we fixed here, this disk will not experience any torque. So K31 is 0. So the required K11, K21 and K31 we could able to obtain when we gave unit displacement at first disk. So this was simpler as compared to the influence coefficient. Now if we want to obtain this stiffness coefficient with second subscript as 2, that is K22, K32. So we need to now shift the unit displacement at 2, keeping theta 1 or disk 1 displacement and disk 2 displacement 0. So the same concept can be applied to obtain these. So I'm not going again to that. So I explained for one of them. For third disk, if you want, for this particular case, we need to give unit displacement to the third disk, keeping other two disk displacement 0. So that will be symmetrically same because as we have done for the first disk, third disk also will be similar. So finally, these are the stiffness coefficient we obtained. And if you see this stiffness coefficients are exactly same if you obtain equation of motion of the system, and if you put the equation of motion in a matrix form, the stiffness matrix elements will be same. If you refer to the equation of motion which I showed in the very first slide, they will match with that. Okay, so I can just show that once. So K11 is this, K12 is this. So all these, I think this should be 0. It should be 0. Okay. So finding stiffness coefficients are easy either through equation of motion directly we can derive or through this procedure. Influence coefficients, finally, whatever we obtained is summarized here. So influence coefficient expressions are more complex as compared to the stiffness coefficients. Okay, so if you have any questions on this, I'll take up some question, and then I think I will stop here. Yeah, Atul.
Good evening, sir.
Hi.
Sir, at page number 20,
Ah.
sir, how the minus sign is comes in?
Yeah, I explain, huh? Because
So this one, sir,
this
T21, sir, T21 is I got means second disk is rotating in an opposite direction, but sir, T31 equal to minus K31. Thus, direction of T11 and T32 is same, sir. So how?
actually the last one is anyway 0. So sign is having no meaning. No, T31 is
Okay,
anyway 0. So don't
okay,
take care of the sign of that. But
okay, sir.
okay, so this is anyway 0.
But sir, if we are taking T32, then it will be negative. It will be positive.
Uh, Actually, here there is no torque. So I should not have shown
Okay,
directly. I could have put 0 here. Because once
okay,
I'm
sir.
fixing this, this is 0. So this should have been 0 directly here rather than.
Okay, okay, sir. Okay, thank you, sir.
Any other question? Any other question? Okay, so today because this particular concept of influence coefficient was applied in the Lagrange's equation, and then I took up one example how to calculate the stiffness coefficient and the influence coefficient, flexibility influence coefficient. So this particular I think particular chapter will continue in the next class on Monday also, where we will take some more examples, and then even we will go for another concept of the transformation matrix, in which actually what happens, we already seen that in a particular system we can have the choice of the generalized coordinate set. We can choose one generalized coordinate set, we can have another generalized set. But only thing is the number of degree of freedom should be number of generalized coordinates should be equal to the number of degree of freedom. So once we have the different choice of the generalized coordinate sets, there is no need to derive the equation of motion for another coordinate system. Once we have one equation of motion in one generalized coordinate, we can able to always transform the equation of motion into another generalized coordinate set. So that transformation, general transformation procedure we'll see, and that transformation is having some meaning because this transformation can make the mass matrix diagonal and stiffness matrix diagonal for a very specific case. So that concept we'll see in the next class. So hopefully by Monday, I think we'll complete this particular transformation matrix. Then we'll go for the eigenvalue problem or the free vibration, finding the natural frequency of the whatever the equation of motion we obtain. Because our main aim is to know whatever the equation of motion we obtain to solve that for finding the natural frequency and the mode shape. So this third chapter is making background for that. So I think, yeah, regarding the exams, I think because on Tuesday, Wednesday you are busy, and 8 to 9 will be too tight for most of you. So I'm planning to have exam on 29th, one day before, on Tuesday, within our usual class timing from 5 to 6. Okay, so because our class is there, so I think no one will object to that. So, and we'll see some, please suggest to Pantha some slot where if required I can take some extra class because I missed one class, and I can take the exam in those slots so that I can not miss the classes because of the quiz. Okay, so please convey that to Pantha so that he can arrange that particular slot for the exams in future. But this quiz one will be on the 29th, that is Tuesday, 5 to 6. Okay, so bye for now.